Coordinate geometry. One of the most elegant ideas in all of mathematics is the idea of the coordinate plane. Other names include the xy plane, the rectangular coordinate plane, and the Cartesian plane. And that final name is in honor of the person who discovered it, the French mathematician René Descartes. Descartes' brilliant idea began by simply putting two number lines at right angles to each other. So of course we know a number line has whole numbers on it, it has fractions, it has decimals, and it goes on forever in both the positive direction and the negative direction. And so what we have here really are just two number lines crossing. The horizontal number line is called the x-axis, the vertical number line is called the y-axis. And of course each one of them goes on forever, each one of them contains positive whole numbers, negative whole numbers, positive fractions and decimals, negative fractions and decimals, the whole 9 yards. The point where the axes cross, 0 on each axis, is called the origin, and that's considered the center of the entire plane. Of course, this allows us to indicate the position of any point on the plane by the x and y coordinate of the point. So for example, we look at this particular point. This particular point is, the point is vertically above x equals 5. So the x-coordinate has to be 5. It is on the same horizontal line as y equals 4. So its y-coordinate is 4. And its position is given by 5, 4. That is the ordered pair that denotes the exact position of that point. As you may remember, 5.4 is an ordered pair with an x-coordinate followed by a y-coordinate. So they're in alphabetical order. First the x-coordinate, then the y-coordinate. Every one of the infinite number of points in the plane can be indicated by a unique ordered pair. So that's amazing fact number 1. You could go to any position in the plane, an infinite number of points in the plane, every single one will have a unique ordered pair, a unique xy coordinate denoting its exact location. On the test, given an ordered pair, you need to be able to locate that point, and given a point, picture of a point, you need to be able to figure out what the coordinates for that point are. So that is an absolutely essential skill. Here's a very simple practice problem. Pause the video and then we'll talk about this. Okay, so this is actually much easier than anything you'll see on the test. It may be that this would be part of another problem on the test. But we want to know, what are the coordinates of this point? Well, first of all, notice that we're to the left of the y-axis. We're on the left side of the xy plane, and so this would be where that horizontal number line is negative. And so the x-axis, because we're to the left of 0, we're in the negative part of that axis, so this is going to have a negative x-coordinate. So we count backwards, 1, 2, 3, 4, 5, 6, 7, and then we count up 1, 2, 3, 4. So that means that the x-coordinate is negative 7, the y-coordinate is positive 4, and the coordinates of that point are negative 7, 4. That is the unique ordered pair which gives the exact location of that point. The axes divide the entire plane into 4 regions known as quadrants. These quadrants are denoted clockwise from the upper right as 1, 2, 3, and 4, and they're almost always denoted with 4 Roman numerals like this. If we know the quadrant of a point, we immediately know the positive or negative sign of both the x-coordinate and the y-coordinate. So for example, in the first quadrant, both coordinates are positive. In the second quadrant, the x's are negative, but the y's are positive. In the third quadrant, both the coordinates are negative at that point. Everything is negative in the third quadrant. In the fourth quadrant, the x's are positive, but the y's are negative. It's also important to note that any point that is exactly on the x-axis or exactly on the y-axis, or certainly the origin, these are not in any of the 4 quadrants. So the 4 quadrants are only for points that are off the axes. Here's a practice problem. Pause the video and then we'll talk about this. Okay, this is a problem that actually could appear on the test because it's a little less straightforward and requires a little bit of visualization. Point M is the midpoint of segment AB. If A equals 2, negative 3, and M is on the negative x-axis, in what quadrant is B? So let's visualize this. We have A here. We don't know where M is, but M is going to be on the negative x-axis, the negative x-axis here. So let's just pick a random point. We could even pick one relatively close to the origin right there. So if A goes to M, well then B would have to be up here. And it turns out no matter where we put M on that axis, we could move it back and forth, B is always going to wind up in the second quadrant. So really, the answer to this question is quadrant number 2. In summary, you need to know the terms: origin, x-axis, y-axis, x-coordinate, and y-coordinate. Those are terms the test will use, and you need to be able to recognize them and know what they mean. It's important to appreciate that every single point in the plane, infinite number of points in the plane, every single one can be noted by a unique ordered pair, a unique set of x and y coordinates. And finally, the axes divide the plane into 4 quadrants. The quadrants of a point determines the positive and negative signs of its x and y coordinates, and the test likes to ask about quadrants. So now we'll talk about graphing lines. You may well remember from high school that a big topic of the xy plane has to do with graphing lines and finding equations of lines. So for example, we might have a line like this. We might have to find the equation of a line, or we might be given an equation and have to produce this line, something along those lines. In this lesson, we'll start with the very basics. This in many ways will just be kind of a conceptual introduction to the idea of graphing lines in the plane. First, we have to focus on a few big ideas before we can actually get to the mechanics of actually how to graph a particular line. So big idea number 1, every possible line in the xy plane has its own unique equation. So there's this, you could say, a one-to-one pairing between a unique line and a unique equation. So that's a big idea. Every line has its own equation. Big idea number 2, for any given line, all the points on the line have x and y coordinates that satisfy the equation of the line. So that's a really big idea. That's a deep idea, and people don't appreciate how deep that idea is. On any line, there's an infinite number of points, all infinity of those points, every single one of them. We could pick out any point at all on that line, find its x-coordinate, y-coordinate, plug it in, and it would satisfy the equation of the line. That is absolutely huge. And finally, big idea number 3, any linear equation that relates x to the first power to y to the first power, as long as there's no multiplication or division of variables or something odd like square roots or something, as long as it's just an ordinary x and an ordinary y and a bunch of numbers, that must be the equation of some line in the xy plane. So for example, we look at this. Y is to the first power, x is to the first power. That has to be the equation of some line in the xy plane, and that's exactly why these are called linear equations. You may remember back in algebra we were referring to these as linear equations. We're referring to them because every single one of them corresponds to a unique line in the xy plane. So let's look at this particular equation. Suppose the problem gave us that equation. We could find values that satisfy that equation, and these would be points on the line. So for example, we could just plug in. If we plug in x equals 0, then we'd see that we'd get 3y equals 12, so y would equal 4. So that means that 0, 4 has to be one point on the plane. Similarly, we could plug in y equals 0. If y equals 0, then we get negative 4 equals 12. We divide, we get x equals negative 3. So that must be another point on the plane. X equals negative 3, y equals 0. So we have 2 points. Technically, 2 points are enough to determine a line. So, for example, if we plot those 2 points and just draw a straight line between them, we get a graph of the line. We were able to draw the line simply by plugging in points, but this is not the most efficient way to plot a line. In the coming lessons of this module, we will learn much more efficient ways to plot the line that represents a particular equation. So we'll get to that, but first we have to make sure that we understand all the basics here. For now, once again, the really big idea is that any point on the line has to satisfy the equation of the line. This idea can be tested in a variety of contexts. So here's a relatively easy practice problem. Pause the video and then we'll talk about this. Okay, we're given the equation of the line, and the equation of the line has this variable in it, the variable k. So we don't know what k is, but we're told that the line must pass through the point 2, 1. Well, we know that that point has to satisfy the equation of the line. So if we plug in x equals 2 and y equals 1, we're going to have to get an equation that works. So we'll do that. We'll plug in x equals 2, y equals 1. What we get is 2k plus 3k. 2k plus 3k is 5k. 5k equals 17. And so k must equal 17/5. So that's the value of k. In summary, every line in the xy plane has its own unique equation. Every point on the line satisfies the equation of the line. And we can figure out the graph of a line by plotting individual points. This is one option, and we will learn other options in the later videos of this module. As we discussed in the last video, every line in the xy plane has its own unique equation. And in fact, this is a miraculous thing about the xy plane, or the Cartesian plane, that it allows us to link equations, that is something in algebra, with shapes, something in geometry. The simplest equations are those for horizontal and vertical lines. Let's think about a typical horizontal line. So here's a horizontal line below the x-axis. Some of the points on this line are 0, -3, 1, -3, 2, -3, so forth. Then -1, -3, -2, -3. And very, very quickly, we see there's a pattern here. The x-coordinate can be any number on the number line, but the y-coordinate has to be -3. They all have the same y-coordinate. A very elegant way to state this condition is simply by saying y equals -3. That's the equation of the line. We specify a horizontal line completely by specifying a y-coordinate. Similarly, any horizontal line will be composed entirely of points of the same height, that is, the same distance above or below the x-axis. If we simply specify that height, the place where the horizontal line crosses the y-axis, then we specify everything about it. Thus, the general form of a horizontal line is y equals k, where k is the height of the line, or k, we could say, is the y-intercept, because wherever it intercepts the y-axis, it just stays at that same y-coordinate. For example, this line here, it intersects the y-coordinate at +2, and in fact, all of its y-coordinates are +2, so the equation must be y equals 2. What is the equation of the x-axis? We don't often think about this, but the x-axis is just a horizontal line like any other horizontal line, and it's a line in the xy plane, so it must have its own unique equation, just like every other line. The x-axis is a horizontal line with a height of 0 because it passes through the origin. It passes through the y-axis at 0. It has a y-intercept of 0. Therefore, the equation of the x-axis is y equals 0. Very, very tricky that the equation of the to write the equation of the x-axis, we need to write y equals 0. Very interesting. Now let's look at vertical lines. Just as horizontal lines have all the same y coordinates, vertical lines have all the same x coordinates. Every coordinate on this line has an x coordinate of 4. And so you can kind of see where this is going. Its equation must be x equals 4. That's the most elegant way to summarize what is essential about that vertical line. The equation of any vertical line that passes through the x-axis at k must be x equals k. So x equals k is the general form of a vertical line. And if we think about the y-axis, that's a vertical line that intersects at x equals 0, so that must have the equation x equals 0. To write the equation of the y-axis, we have to use an x. Again, very interesting. Any 2 points that share the same y-coordinate must lie along the same horizontal line. Any 2 points that share the same x-coordinate must lie along the same vertical line. If point C has the same x-coordinate as point A and the same y-coordinate as B, then that angle ACB has to be 90 degrees because any horizontal line is perpendicular to any vertical line. Keep in mind that a horizontal line can go through quadrants 2 and 1, or it can go through quadrants 3 and 4. A vertical line could go through quadrants 3 and 2, or it could go through quadrants 4 and 1. Most horizontal and vertical lines move through just 2 quadrants. As we'll see later on, most slanted lines move through 3 quadrants. We'll talk about that later. Also, keep in mind that while most distances in the xy plane are slightly harder to find, and we're going to have a video on that later, vertical and horizontal distances are very easy to find. All we have to do is subtract. What's the distance between 5, 1 and 5, 8? Well, they're both on the same horizontal line, and so the x-coordinate doesn't change at all. They're on the same vertical line, sorry. The x-coordinate doesn't change at all. The only thing that changes is the y-coordinate, so it's just a vertical distance of 8 minus 1, which is 7. What's the distance between -3, 2 and -9, 2? Those are on the same horizontal line. They have the same y-coordinate. And so we just have a horizontal distance from -3 to +9. And when we go from -3 to +9, 9 minus -3 is 9 plus 3, which is 12. Here's a practice problem. Pause the video and then we'll talk about this. Line P shown in the diagram is a horizontal line in the xy plane. Line Q not shown is perpendicular to line P and passes through the point 5, 7. What is the equation of line Q? So line Q is on this line here, and we know that every vertical line has the same x-coordinate. So we know it's a vertical line. All vertical lines have the same x-coordinate, so it is of the form x equals k. Well, what's the x-coordinate? Well, if it goes through 5, 7, it must have an x-coordinate of 5. X equals 5. So this is actually a relatively straightforward problem. This is actually a little bit easier than something that the test would ask, because that just focused on horizontal and vertical lines and nothing else. Here's another practice problem that's slightly more test-like. It combines the information about horizontal and vertical lines with some ideas from other sections. Pause the video and then we'll talk about this. In the coordinate plane, the line x equals 2 and the point 7, 3 are shown.
What is the equation of a horizontal line above the point 7, 3 that is as far from the point 7, 3 as is the line x equals 2? So first of all, we have to figure out the distance between this point and this line. Well, typically the way we do that is figure out the direct perpendicular distance. This has an x-coordinate of 2, this has an x-coordinate of 7, so this distance here is 5. And so what would happen if we had a line, a horizontal line above this point that was also a distance of 5? Well, this is at a y-coordinate of 3, and so it would go up to a y-coordinate of 8. It would go up to the point 7, 8. That would be the closest point. And so the y-coordinate would be 8 of that horizontal line. A horizontal line is always of the form y equals k. The k has to be 8. And so it has to be y equals 8. Answer choice C. Horizontal lines have the general form y equals k. Vertical lines have the general form x equals k. The x-axis is y equals 0. The y-axis is x equals 0. Very important to keep in mind that interesting swap. If 2 points share the same x-coordinate, they are vertically separated. If 2 points share the same y-coordinate, they are horizontally separated. Now we'll talk about slope. And in many ways, slope is the single most important idea to understand about lines in the xy plane. And of course, the test likes to ask about lines in the xy plane, so it's very important to understand slope. Slope is roughly a measure of how steep a line is. So in other words, if a line is almost flat, then it has a low slope, but if it's going up like this, it has a higher slope. Different lines are at different angles, and slope is a way about talking about their slants. So before we get into slope, I'll say throughout coordinate geometry, it's important to think about concepts and problems with 3 different perspectives. Numeric, what's going on with actual numbers of coordinates. Geometric, what does the picture look like? And algebraic. And of course, many students tend to over-focus on the algebraic and neglect the numeric and geometric. And this produces a limited understanding, and folks don't realize this. They get very comfortable with the algebra, and they say, I want to do algebra, I want to do algebra, and they don't realize what they're missing. And so if you really want to understand slope deeply, you need to have all 3 of these perspectives. And in fact, for the very important idea of slope, the geometric and numeric perspectives are the most important, and the algebraic perspective is the least important of the 3. And again, this is paradoxical. People get a formula and think, oh, well, if I have a formula, I really understand something. It turns out that algebra is not the perspective that gives you the most insight into what slope is. And it's much more important to think about the geometric and numerical perspectives if you really want to understand this important idea deeply. Okay, let's talk about slope now. One of the most common definitions is rise over run. What does this mean? Suppose we want to find the slope between 2 points. The run is the horizontal separation from left to right. This is always positive from left to right. The rise is the vertical separation between the 2 points as we go from left to right. If the point on the right is higher, then the rise is positive. If lower, then negative. And so run is always horizontal, rise is always vertical. Suppose we want to find the slope between 2 points. A good geometric way to approach this is to construct what I will call a slope triangle. This consists of a slanted segment between 2 points, a vertical leg and a horizontal leg. So point 1 and point 2, those are the 2 points between which we want to find the slope. The hypotenuse there is the line that actually has the slope that we're looking for. And then there are 2 legs, a vertical leg and a horizontal leg. And of course, the vertical leg is automatically the rise, and the horizontal leg is automatically the run. So if we construct this triangle immediately, geometrically, we get the rise and the run. For example, suppose we want to find the slope between 2, 2 and 6, 5. We draw or imagine a little slope triangle. And again, You might be able to just visualize this, but even if you can't, you can sketch this on the scrap paper. It just has to be a rough sketch. And so now we have a slope triangle, and of course, as always, the horizontal leg is the rise. Sorry, the horizontal leg is the run, the vertical leg is the rise. And we see, of course, this is a line that's going to have a positive slope. It has a positive rise. So again, the run is the horizontal leg, the rise is the vertical leg, slope is rise over run. Well, what is the rise? Well, the rise, we go from the line y equals 2. We go from that line at the bottom up to y equals 5. And so the vertical distance along that vertical leg is 3. 5 minus 2, which is 3. The rise is 3. The run, we're going from x equals 2 to x equals 6. And so the distance along that horizontal line, 6 minus 2, is 4. So the rise is 3, the run is 4, and the slope is 3/4 or 3/4. Suppose we want to find the slope between -4, 2 and 5, -1. Again, we draw the slope triangle. Again, the horizontal leg is the run, the vertical leg is the rise. Here, notice that the point on the left is higher. And so this actually has, as we move from left to right, we actually have a drop. In other words, the rise is negative. We go from a height of y equals 2 down to y equals -1. And 2 minus -1 is 3. That's actually a drop of 3. And so that is the rise. The rise is -3. And then, of course, the run, we're going from -4 to +5. That's a distance of 9. So the run is 9. Rise over run, -3 over 9. We simplify the fraction to -1/3. If you are given the numerical coordinates at 2 points, I would suggest using the slope triangle to find the slope. In other words, practice using the geometric perspective. Sometimes you're given an algebraic formula and you have to use the formula for the slope, and so there are times when it is appropriate to use the algebra, but don't make the formula your default. Don't use algebra 100% of the time. This is one of the many examples in which over-reliance on a formula produces a shallow mathematical understanding. And this is something so hard to understand because people get so excited about memorizing formulas. They think if I know a formula, I know something, and they don't realize that over-reliance on that formula actually inhibits them. Having warned you about the perils of over-reliance on the formula, I will give the formula. Suppose we have two general points, x sub 1, y sub 1, x sub 2, y sub 2. And if we're given two sets of coordinates, it actually doesn't matter which one we call point 1 and point 2. It doesn't matter at all. One of the points is point 1, one of the points is point 2. The run is the difference of the x coordinates. The rise is the difference of the y coordinates. Again, the only thing that matters is we subtract in the same order. Here we're subtracting point 2 minus point 1. We have to do that both in the rise and the run. Then we just put rise over run. And that is the slope formula. And so if you're going to use that formula, make sure you understand its deep connection to the idea of rise over run. Don't memorize it as an isolated factoid, but understand how it's connected. So far, we've been talking about the slopes of two individual points. A line has a slope, and in fact, the slope of a line is the slope between any 2 points on the line. If a line has a slope of 1/2, for example, then if we pick any 2 points on the line, the ratio of rise over run will simplify to 1/2. So that's really important. That is part of the magic of a line, that you could pick any 2 points at all on that line, and the slope between those 2 points would always be the same. Let's think about a slope of 2. What exactly does a slope of 2 mean? And here we're going to be thinking more about a numerical perspective. So a slope of 2 could mean that we go right 1 unit and then up 2. So that would be a slope of 2. We could go right k units and up 2k units. So we could have any proportion that we wanted. For example, we could go over 7 and then up 14, something like that. But it also means that we could go the other way. We could go left 1 unit and down 2 units. That's also a slope of 2. Or we could go left k units and down 2k units. So any proportion. We could go left 5 units and down 10 units, that sort of thing. If the point -3, -1 is a point on the line with a slope of 2, then if we go over 1 up 2, then we go to -2, +1. Again, if we start at -3, -1, and if we go left 1 and down 2, then we get to -4, -3. So if you know the slope and you know an individual point on the line, it should be very easy to find other individual points. Again, this is a numerical perspective on the slope. Let's think about a slope of -2/3. Well, that one piece of information contains so much information in it. So it certainly could be a run of 3 and a rise of -2. So in other words, we go right 3 units and down 2 units. So that's certainly true. It also means we could go right 3k units and down 2k units, any proportion of that. It also could mean that we go right 1 unit and down 2/3 of a unit. Sometimes we only want to make a small change and we want to see the fractional change in y. So we could also use that form. It means that we could go the other way with all of these. We could go left 3 units and up 2 units. We could go left 3k units and up 2k units. Or we could go left 1 unit and up 2/3 of a unit. And again, we'd use the fractional form when we were moving very small distances and we wanted to see a very small change in y. Here's a practice problem. Pause the video and then we'll talk about this. Okay, a line goes through 2, -1 and has a slope of 5/3. Find all the points A, B on the line where A and B are integers whose absolute values are less than or equal to 10. So here we're going to start with the point 2, -1, and we're going to start by moving to the right. So we're going to move right 3 and up 5. So 2, -1, if we move right 3, we move from 2 to 5. If we move up 5, we move from -1 to 4. So this gets us to 5, 4. We do that again, we move from 5 to 8, and we move from 4 to 9. So we get to the point 8, 9. And then if we do it again, we're going to wind up with values bigger than 10. So we want to get those 2 points in that direction. Now go back to the original point. Now we're going to move left 3 and down 5. So if we start at an x of +2, move left 3, we're going to get to -1. We start at a y of -1, move down 5, we're going to get to -6. So we get to -1, -6. And then if we move left 3 down 5 again, we're going to get to -4, but -11. And again, we have an absolute value bigger than 10, so there's in fact only 3 points that satisfy this condition, and we found the coordinates of all 3. Notice that if a line has a slope of 1, then rise equals run, and the slope triangle is a 45, 45, 90 triangle. You should know that lines with slopes of 1 or -1 make 45-degree angles with the axes. That's something you should know. You don't have to worry about the exact angles formed by any other slanted lines. Simply notice that lines with a slope of greater than 1 or less than -1, that's an angle of more than 45 degrees, so those are steeper than any road that you might walk or drive on. In fact, one very good way to think about slope is think about the roads that you typically walk on or drive on, the hills that you climb up, that sort of thing. See if you can figure out the slopes of those. That's a very good way to develop not only a visual but even a kinesthetic sense of slope. What is true if 2 lines are parallel? What's true about the slope of parallel lines? If the lines are parallel, they must rise and sink, same rise for the same run. In other words, parallel lines have to have equal slope. So that's the very intuitive idea. Everyone kind of gets that parallel lines have equal slope. That's the one that has a lot of appeal to it. Perpendicular lines, this is a little bit harder. What is true if 2 lines are perpendicular? First of all, one goes up, the other goes down, so that means that they have to have opposite signs. If one is positive, the other is negative. Opposite signs is part of the answer, but we need to think about the numerical value of the slope. Think about what happens when we rotate the slope triangle by 90 degrees. So the blue triangle is the original slope triangle, the dark blue triangle. The light blue triangle above is the rotated slope triangle. And now notice that what was the original rise is now the run. And what was the original run is now the rise. So in other words, rise and run swapped places, or numerator and denominator swapped places. Well, what do we call that when numerator and denominator swap places? We call that a reciprocal. And so the slopes of perpendicular lines are opposite-signed reciprocals. So that's a hard idea to understand. In other words, if the slope of the original line is P over Q, then to get the perpendicular line, we have to flip the fraction over and add a negative sign, negative Q over P. So the original slope is 1/2, then the perpendicular slope, 1/2 flipped over, the reciprocal of 1/2 is 2, and then we have to put a negative sign to it. So positive 1/2 and negative 2, those are two perpendicular slopes. So let's practice finding perpendicular slopes. In fact, pause the video here and see if you can find, for all these M1s, what would be the slope of the line perpendicular to it. Pause the video and then we'll talk about this. Okay, for the first one, the reciprocal of 5 is 1/5. So the opposite sign reciprocal would be negative 1/5. So a slope of 5 and a slope of negative 1/5, those are two perpendicular slopes. For the second one, the reciprocal of 3/7 would be 7/3, and so we'd have to make that negative. So it would be negative 7/3. For the third one, it's already negative, so we're going to have to make the negative into a positive. And of course, the reciprocal of 11 over 8 is 8 over 11. So it would be positive 8 over 11. And finally, we have a slope of negative 1/20. Well, the reciprocal of 1/20 is just 20. And because it's negative, the original is negative, we have to make the perpendicular slope positive. So it would be positive 20. And so again, when we're finding perpendicular slopes, we have to take the reciprocal, that is, flip the fraction upside down, and change the sign. Change it to an opposite sign, positive to negative or negative to positive. In summary, slope is rise over run, and that is a very powerful definition. It lends itself well to slope triangles. We find the slope between 2 points with a slope triangle or with the slope formula, and again, thinking about the geometric and numerical perspectives is very, very helpful with slope. The slope of a line is the slope between any 2 points on the line. Lines with a slope of plus or minus 1 make 45-degree angles with the axes. Parallel lines have equal slopes, and perpendicular lines have slopes that are opposite sign reciprocals of each other.
Let's talk about intercepts. Just to orient ourselves exactly where we are in math world right now, we're talking about coordinate geometry, so that's x and y axis. And what this is all about is translating algebraic functions onto graphs, right? We use x and y points, and we can make a graph from that. So just as an example, let's take a nice easy function here, y equals 2x plus 1. So what we could do is pick out a few points that would appear in this function, i.e. some points that satisfy this function. I don't know, what happens if we plug in 1 for x? Well, let's see. If we plug in 1 for x, then that becomes y equals 2 times 1 plus 1, so 3. And again, this is just some review here. And we can do the same thing for 2, and when we do that, I'll invite you to do it on your own. It spits out 5. When you plug in negative 1 for x, it spits out negative 1. And when you plug in 0, it spits out 1. And so we can take all those points and put it on a nice, pretty graph like this, and we can identify them on the graph. See, we got 1, 3 right there. There it is, 1, 3. And we got 2, 5 right there. We got the point negative 1, 1. Negative 1, 1. And the point 0, 1. Now, this particular lesson, I'll write that in, 0, 1. This particular lesson focuses on this type of point. That is an intercept. An intercept is where the graph meets one of the axes, be it x or y. And so that's our definition, right? An intercept is the point at which a graph crosses the x or y axis. So if I take my, my graph that I was just looking at and zoom in on it a little bit, I'm interested in the points where this graph crosses the y-axis and the x-axis, right there and right there. But let's get a little more mathematical about this. At the y-intercept, the value of x is 0. And we can see that, right? This is the point 0, 1. And conversely, at the x-intercept, the value of y is 0. What point is that? Well, it's the point negative 0.5, 0. Right? The y value here is 0. And that's it, right? They're going to make this a little more complicated, but let's take a look at what you could see on the test. Very often, you're going to be asked to find the intercepts from an equation. So why don't we use the one we were looking at before? Y equals 2x plus 1. And again, that's what the graph looks like, just for reference, but we're going to be doing this so that you don't even have to graph it. We know that the graph crosses the y-axis when x equals 0. That's what we talked about. So essentially what we're asking is, what is the value of y when x equals 0? Okay, well, why don't we just plug in 0 to this equation? Y equals 2 times 0 plus 1. So that's 0 times 2, 0 plus 1. It's 1. And so the y-intercept of this equation is 1. I didn't even need to graph it. You'll note, if you know your linear functions well, that the y-intercept is always the b in the y equals mx plus b equation. But that's for another lesson. Feel free to check out linear functions for that. All right, but how about the x's? So suppose we want to know what the x-intercept of this line is. Well, if the x-intercept is where y equals 0, then all we got to do is plug 0 in for y. So let's do that, right? In this case, it's going to be 0 equals 2x plus 1. So we have to do a little more algebra here. Let's subtract 1 from both sides. There we go. We got negative 1 equals 2x. Divide both sides by 2, right there, and I get x equals negative 1/2. And sure enough, that's what we see on the graph, right? So we don't even need the graph to calculate what the x-intercept is. So let's do some practice here just to make sure we have the hang of it. What is the x-intercept of the function y equals 7x plus 14? So you can go ahead and stop the video right now if you want to do this on your own. And now we'll do it together. Okay, we're looking for the x-intercept. That means the point where y is 0. So how do we find that? Well, we talked about this. We just plug 0 in for y. So I say 0 equals 7x plus 14. And then I'm going to subtract 14 from both sides. There we go. And that gives me negative 14 equals 7x. So now I'm going to divide both sides by 7. And that leaves me with x equals negative 2. So the x-intercept of this line is negative 2. Put differently, as a point, that's negative 2, 0. All right, let's do another one here. What is the x-intercept of the function y equals 3? So if you want to try this on your own, go ahead and pause the video here. And now let's do it together. Okay, so again, we want the x-intercept, just like before, right? So let's do what we did before and plug in 0 for y. Well, 0 equals 3. What does that mean? I mean, when will 0 equal 3? Well, the answer is never, right? At least not in this universe. There's no case where the number 0 equals the number 3. So what does that mean? Well, it means that there is no x-intercept. kind of a tricky question, right? But if you want to see this on a graph, here's what it looks like. If we graph the function y equals 3, all we're saying is y equals 3 no matter what x is. When x is negative 4, y is 3. When x is negative 2, y is 3, and on and on and on and on. So this graph does not cross the x-axis, and therefore it does not have an x-intercept. We can see that graphically and algebraically. And finally, this one. Which equation could be represented by the graph below? So go ahead, put the video on pause again, and then we'll take a look at it together. All right, here it goes. So at first blush, this looks like a pretty difficult problem. We have some wild exponents here. We got a curvy graph. What are we supposed to do? Well, very often on the test, you can eliminate most or even all of the incorrect answers just by focusing on the intercepts. What do I mean by that? Well, let's take a look at this, right? This is the y-intercept of this graph. It's where the graph crosses the y-axis. And I don't know exactly what that number is, but I do know that it's negative, right? That's a negative number. So that means if I plug in 0 for x, I should be left with a negative number. Well, let's see what happens when we do that. Plug in 0 for x right there. Goes away. 0 cubed is 0. Plug in 0 for x right there. That whole expression goes away. And what am I left with? Well, negative 7. So that could work. That could be the y-intercept. What happens if we do it for b? Plug in 0 there, goes away. Plug in 0 there, goes away. Plug in 0 there, goes away. Nope, that doesn't work. That's a positive number. I need a negative number for my y-intercept. All right, how about here? Plug in 0 right there and 0 right there. And negative 3 times negative 7 gives me positive 21. No thanks. I need a negative number. And then finally, if I plug in 0 right there, that goes away, and I'm left with 3. Doesn't work. So just by testing the y-intercept, I know that the correct answer to this problem is A. And so the takeaway is, when you see a complicated graph, one of your first checks should be about the y-intercept. Very often you can eliminate most or all of the incorrect answers using that. Correct answer to this one is A.
Now we can talk about slope-intercept form, in other words, y equals mx plus b form. The equation of any line can be stated in several different algebraically equivalent forms. We could have x and y on the same side, or solve for x, or solve for y. These algebraic changes don't change the underlying mathematical information. No matter how we rearrange the algebra, it's always the same line that's represented. That's an important idea. Of all possible algebraic representations, mathematicians have selected one as particularly useful. If we solve the equation of a line for y, getting y on one side by itself equal to everything else, then we automatically put the equation into what's called slope-intercept form, or y equals mx plus b form. In this equation, y equals mx plus b, m is the slope of the line and b is the y-intercept. If we solve the algebra for y, we automatically get these two very important quantities, the slope and the y-intercept. We can see that m must be the slope because when x increases by 1, y has to increase by m. We can see that b must be the y-intercept because if we set x equals 0, then y equals b. It's easy to put any equation into slope-intercept form, and once it's in that form, it's easy to understand where the graph will go. Starting from the y-intercept, we can take slope steps that we discussed in the slope lesson. 1 unit to the right up m slopes, or 1 unit to the left down m slopes, etc. Here's a practice question. Pause the video and then we'll talk about this. Okay, find all the points jk on the line y equals negative 4/3 x plus 2, such that j and k are both integers with absolute values less than or equal to 10. So this is in y equals mx plus b form. The slope is negative 4/3. The y-intercept is positive 2. And so that's the point 0, negative 2. So that's actually one of the points. That's one point that satisfies this condition. Both the coordinates are integers, and they both have absolute values less than or equal to 10. Now, what does a slope of 4/3 mean? Here we're going to take the numerical perspective on slope. Slope means move right 3, down 4. Or it could mean move left 3, up 4. So if we start at the point 0, 2, then if we move right 3, down 4, we go from 0 to 3 and down from 2 to -2. If we go right 3, down 4 again, we'll get to 6, and then down 4 more, down to -6. Right 3, down 4 again, we'll get to 9 and -10. So we have to stop there because we've reached an absolute value of 10. But all of those points work. Now go back to 0, 2. Now we're going to go the other way. We're going to go backwards 3 to the left 3 and up 4. So that would bring us to -3, 6. And then again, -6, 10. And we have to stop there because again, we've reached an absolute value of 10. And so there are 6 possible points. Here are the 6 possible points that satisfy this condition. They're on that line, and they have x and y coordinates that are integers, and both the x and y coordinates have absolute values less than 10. Here's another practice question. What is the slope of the line with the equation 3x plus 5y equals 8? So that's one way to write it. So all we have to do is solve for y. So we're going to start here. First, we'll subtract 3x from both sides. Now we're going to divide everything by 5. Remember, when we divide by 5, all 3 terms get divided by 5. And so we get a slope of -3/5. In fact, we also find out that the y-intercept is 8/5. That wasn't asked, but that information is kind of tossed in as a bonus. Notice that horizontal lines have a slope of 0 because they are all run with no rise. If a horizontal line has a y-intercept of -4, then m equals 0 and b equals 4. And so the slope-intercept form for this line would be y equals 0 times x plus 4, or in other words, just y equals 4. The default form for a horizontal line can be interpreted as a kind of slope-intercept form. It's what happens when slope equals 0. Now, vertical lines are very different. First of all, because vertical lines have undefined slope, because the slope fraction is always something over 0. So you could say they have infinite slope or undefined slope. Furthermore, vertical lines run parallel to the y-axis, and typically they never intersect the y-axis, except for the y-axis itself. Any vertical line that is not identical to the y-axis never intersects the y-axis. So the standard form for vertical lines, x equals k, is completely unrelated to slope-intercept form. It's its own thing. Here's a practice problem. Pause the video and then we'll talk about this. A couple of videos ago, we talked about how if you were given the x and y coordinates, the x-intercept, the y-intercept of a line, we could find the equation of the line. And that's exactly what this problem is asking us to do. So first thing we're going to say is we're given the x-intercept, so we know that. We have a little slope triangle drawn right here. It's formed by the axes right here. And we have a run of 5 and a rise of -2. And so we have b equals 2, a rise of -2, a run of 5, and we get a slope of -2/5. So now we can write the equation of the line, y equals mx plus b, y equals -2/5 x minus 2. All right, very good. But now we go back to the answer choices and we see that's not listed. We have integers times x and y, and the x and the y are on the same side of the equation. All right, so how do we do this? Well, first, we're just going to multiply everything on both sides by 5 to get rid of the denominator. So we get a 5y equals -2x minus 10. Then what we're going to do is add 2x to both sides. So we get 5y plus 2x equals -10. Now we go back to the answer choices, and we recognize answer choice D. In summary, if we solve the equation of any line for y, we automatically put the equation into slope-intercept form, y equals mx plus b, where m is the slope and b is the y-intercept. This form makes it easy to graph the line and understand where it goes.
Writing equations of lines. Sometimes the test will give you information and ask you to come up with the equation of a line. In other questions, solving for the equation of the line will be very helpful in finding what the question asks. The test could expect you to find the equation of a line either from numerical information, here's the value of the slope, here's a point, here's the y-intercept, that sort of thing, or they could give you a picture. If you are given a picture of the line, it should be relatively easy to read both the slope and the y-intercept from the picture, and these will allow you to create the equation. Here's a practice problem. Pause the video and then we'll talk about this. Okay, the line shown passes through the point a, 30. What is the value of a? Well, it's very easy to read off this graph the value of the y-intercept. The y-intercept is 1. And the slope, well, since it goes through -2, we have a run of 2 and a rise of 1. So rise over run would be 1/2. So the slope is 1/2 and the y-intercept is 1. So that means this has to be the equation of the line, y equals 1/2 x plus 1. Well, now we have an equation, so now we can plug in. We plug in a for x and 30 for y, subtract 1, and then multiply by 2 to cancel the 1/2, and we get a equals 58, and that's the answer. The test could give you the slope and then some point on the line. The slope and a single point are enough to determine a unique line. You can plug the slope directly into the slope-intercept form, y equals mx plus b, so we would know m. We would initially not know the value of b, but because every point on the line must satisfy the equation of the line, you can plug in the coordinates of the given point for the x equals y in the equation, and that will give you an equation you can solve for b. And once you solve for b, you have full slope-intercept form. So here's a practice problem. Pause the video and then we'll talk about this. Okay, so what we're given here is a slope. We have a slope of -5/3, and we get a point on the line, -2/7, and we want to know what is the x-intercept of the line. Well, we have two very different ways of going about this, and I'm going to show them both. The first is what I would call an algebraic solution. So here we're going to write y equals mx plus b. We know the m, so we're going to plug in the slope of -5/2, and we're also going to plug in the coordinates of the point, x equals -2 and y equals 7. We're going to plug that in. This will give us an equation for b. Of course, -5/3 times -2 is +10/3, and then b would be 7 minus 10/3. We find a common denominator, and then we subtract, and we get the y-intercept. So now we have the full slope-intercept form, the full y equals mx plus b form. Now, what we need to find is the x-intercept. Well, of course, the way we find the x-intercept of a line is to set y equal to 0 and solve for x. So multiply by 3, and we get an x-intercept of 11/5, or 2.2 as a decimal. So that is a completely algebraic way to solve the problem, and that's a perfectly correct way to solve the problem. That will get the answer. I also want to show a completely different way of thinking about this problem, what I would call a graphical solution. So we know that it goes through the point -2, 7. Well, let's think about this slope. What does that slope mean? If we want to get closer to the y-intercept, because it has a the x-intercept, we need to move to the right because it has a negative slope. So if we move right, then it will move down. And so we could move with a run of 3 and then drop the height by -5. That would be a slope of -5/3. And so that would mean we move, the x goes up by 3, so it goes from -2 to +1, and the y goes down by 5, so it goes from 7 down to 2. So now we're a lot closer to the x-axis. Now let's think about that visually. We have the point 1, 2, which is on the line. Then there's the x-intercept. And notice that little triangle that we make there, that has to be a slope triangle. So in other words, if we just look at the absolute values, 2 over b, that's a rise over run. 2 over b, that has to equal the absolute value 5 over 3. Well, that allows us to solve for that little b there. We get b equals 6/5. Now, let's think about this. We want the x-intercept. Well, we know the distance from the origin to 1, 0. That's a distance of 1. And then the distance that I'm calling b there is a distance of 6/5. So we'll just add, so the 6/5, I'll write that as 1.2 for simplicity. 1.2 plus 1, that would be an x-intercept of 2.2. So that is a graphical way of approaching this. Now that might be an unfamiliar way. That's typically not the way they teach you to approach things in school. But I would point out, if you can solve the problem algebraically and also solve it graphically using proportions, then you really understand it very deeply. It will enormously enhance your understanding of coordinate geometry to think about both approaches. The test could give you 2 points and expect you to find the equation of the line. 2 points uniquely determine a single line. So if you're given the 2 points, what do you do? Well, of course, from the 2 points, we can always find a slope. And then once we have the slope, again, what we'll do, we'll plug either one of those points. It doesn't matter. Either one of those points for the x and the y in the equation, plug the slope in. We can solve for b, and then we have full slope-intercept form. Once you have the slope, you may be able to think about the question graphically as well. Here's a problem. Pause the video and then we'll talk about this. Okay, line J passes through the points -3, -2, 1, 1, and 7, Q. Find the value of Q. Well, again, we have a couple ways of thinking about this. The first solution I'm going to show is an algebraic solution. So we need to find the slope. That's primary. We find the slope from those 2 known points between -3, -2, and 1, 1. We have a rise of 3 and a run of 4. So rise over run is 3/4. So that's the slope. Now we'll plug that in to y equals mx plus b. We can plug either one of the points in. I'm going to say that plugging 1, 1 is going to be much easier than plugging in -3, -2. I get to choose, so I'm going to choose the easier one. I'm going to plug in 1, 1, and then just solve for b, and I get b equals 1/4. So then I get 3/4 x plus 1/4. That is slope-intercept form. So now I have the equation of the line itself. I have the equation of line J. Well, now I'm just going to plug in to find Q. I'm just going to plug in 7 for x, Q for y, multiply everything out, and what I get is 22 over 4. Of course, I can simplify that. That becomes 11/2. So that's one way to solve the problem. Again, that is a perfectly valid way to solve the problem. Incidentally, I can also write 11/2 as 5.5. Algebraic solution will always get you to an answer. But here's another way to think about it. We're going to use a graphical solution. So again, you have to find the slope. The slope is primary information about the line. If it's available to find the slope, always find the slope. It always helps you. All right, so now let's think about this. We go through the point -3, 2. We go through the point 1, 1. We want to get a little closer to that point 7, Q. So I'm going to go over 4 and up 3. And so that will put me at 5, 4. And then I'm reasonably close. So now from 5, 4, of course, the run going from 5 to 7 is 2. So that little slope triangle there has a run of 2. We'll call the height of it h. And it must be true that rise of a run, h over 2, equals the slope of the line. H over 2 has to equal 3/4. So we set up this proportion. We solve for h. H equals 3/2. 3/2, I can write that as 1.5. So now we can figure out the height of Q. So the bottom of the slope triangle, this diagram, is at a height of 4. And then to get up to Q, it's just 4 plus h, or 4 plus 1.5, which gives us 5.5. So that is a graphical way of solving the exact same question. Again, when you're doing your practice, if you can solve it algebraically and also use proportions to solve it graphically, you will have a much deeper understanding of coordinate geometry. If we're given a well-labeled graph, we may be able to read the slope and the y-intercept from the graph itself. That's a big idea. Once we're given 2 points, we can find a slope. Once we have a point and a slope, we can plug these into y equals mx plus b to solve for b. And remember, you often have the option of solving algebraically or graphically, thinking about the proportions involved with the slope. And again, if you can solve the problem both ways, with an algebraic solution and a graphic solution, you understand this topic extremely well. Sometimes the test gives 2 points and asks us for the distance between them. Other times we will need to find distance in the xy plane in the course of answering a geometric question. Something like, is the triangle isosceles? Something like that. Or is the figure a square? Big idea number 1. In the xy plane, horizontal and vertical distances are very easy to find. If 2 points are on the same horizontal line, all we have to do is subtract the x-coordinates. We subtract bigger minus smaller because distance is always positive. If 2 points are on the same vertical line, we subtract the y-coordinates. Incredibly easy. We can't do anything this simple if the 2 points are separated by a slanted line. Let's think about 2 points diagonally separated. So, for example, suppose we have this. So we can't just do any kind of subtraction, but think about it this way. If we draw the slope triangle we were using to find the slope, remember the slope triangle, suddenly things become much clearer. Okay, so here are the same points again, but now we've drawn a slope triangle. Well, it's very easy to find the rise and the run in that slope triangle. The rise is 3. We can see the vertical leg has a distance of 3, a length of 3. The horizontal leg, the run, has a length of 4. So if the horizontal leg is 4 and the vertical leg is 3, this is just a 3, 4, 5 triangle. And so the distance between those 2 points, the hypotenuse, has to be 5. Now, it won't always be the case that the 3 sides of a triangle are nice, neat Pythagorean triplets, although this is quite common on the test. Nevertheless, it will always be the case that the slope triangle is a right triangle. By definition, the slope triangle is a right triangle. The horizontal and vertical legs have lengths that are easy to find, and the length of the diagonal will always be the hypotenuse of the slope triangle. We can always find that length by the Pythagorean theorem. So we're using the Pythagorean theorem to find the distance between any 2 points. That's big idea number 2. Here's a practice problem. Find the distance between those 2 points. Pause the video and then we'll talk about this. Okay, so if we find the x leg, the run between them, we get a run of 8 and a rise of 4, a y leg of 4. We could do the Pythagorean theorem with legs of 4 and 8, but it's easier if we scale down first by the greatest common factor, a scale factor of 4. We scale down to a much smaller triangle with legs of 1 and 2. Well, that's very easy to solve. If we have legs of 1 and 2, we square those, we get c squared equals 5, c equals the square root of 5. Now we'll scale back up by a scale factor of 4, and we get a hypotenuse on the larger slope triangle of 4 root 5. And that's the distance between those 2 points. So notice that we could use proportional thinking to really simplify that calculation. Now there is a formula known as the distance formula. I absolutely refuse to teach it, and even if you know it, I encourage you not to use it. I think sticking to this formula is actually ultimately a more time-consuming way that impedes understanding. And you understand much more deeply if you think about it the way I'm showing in this video using the Pythagorean theorem. So if you use the Pythagorean theorem to find the hypotenuse of a slope triangle, you're thinking visually, and you can also use the proportional thinking to simplify your calculation. Of course, using the slope formula the distance formula would not allow you to do that. So there are a variety of reasons that using the formula is an exceptionally bad idea, and it's much better to think about this situation carefully. When you do think visually about the xy plane, you understand much more deeply than when you simply plug into a memorized formula. Now we can talk about circles in the xy plane. Of course, according to its fundamental definition, a circle is the set of all points equidistant from a fixed center. Everything we said about distance comes into play with circles in the xy plane. Here's a practice problem. Pause the video and then we'll talk about this. Okay, a circle in the xy plane has a center of 6, 3 and a radius of 5. Find the 2 x-intercepts. Think about the 2 radii that go from the center to these 2 x-intercepts. Each radius has a length of 5, and it's the hypotenuse of a slope triangle. Also, the point 6, 3 is clearly 3 units above the x-axis. So let's think about all this visually. So we have those 2 little triangles there. Each one has a hypotenuse of 5, and it's a distance of 3 above the x-axis. So that vertical length is 3. Well, of course, what we have there are 2, 3, 4, 5 triangles. So the horizontal lengths each have a length of 4. And so starting at 6, we go 4 to the right and 4 to the left. We get 2 x-intercepts of 2, 0 and 10, 0. And those are the x-intercepts. If the circle is centered at the origin, then the slope triangle of each radius has a horizontal leg of the absolute value of x and a vertical leg of the absolute value of y, regardless of what x and y are. Thus, the equation for a circle with center 0, 0 and radius r must be x squared plus y squared equals r squared. So notice that we're really just doing the Pythagorean theorem to find the equation of a circle. So horizontal and vertical distances in the xy plane, we just use subtraction. Very easy. For slanted distances, we draw or imagine the slope triangle and use the Pythagorean theorem. The distance between the 2 points is the hypotenuse of the slope triangle. Remember Pythagorean triplets. Remember to use scale factors to simplify your calculations, all those things we talked about back in the geometry lessons. For a circle in the xy plane, each slanted radius forms a slope triangle, and all these slope triangles have equal hypotenuses because the hypotenuse is the radius. The equation of a circle with radius r centered at the origin is x squared plus y squared equals r squared. Now we'll talk about a bit of an odd topic, reflections in the xy plane. Questions about reflections of points are not very common. They appear mostly in the more advanced questions, but if we understand a few simple principles, these rare and challenging questions become quite easy. First, we need to review a couple ideas from pure geometry. Suppose we reflect a point over a line and then draw a segment between the original point and its reflected image. So we have an original point, reflected image, and we draw a little segment, that green segment, connecting them. Of course, the original and the reflected are equidistant from the line, but more than that, the mirror line is the perpendicular bisector of that segment. That's a big idea, that a mirror acts as a perpendicular bisector. As you may remember from the geometry module, every point on the perpendicular bisector of the segment is equidistant from the two endpoints of the segment. This means that every point on the mirror line is equidistant from the original point and the reflection. These properties are true for all reflections. So these are really big ideas. So let's talk about reflections over the x-axis. If we reflect a point in the xy plane over the x-axis, the original point and the reflected image will have the same x-coordinate. It will be on the same vertical line. The y-coordinate has equal absolute values and opposite signs. So we just take the y-coordinate. If it's positive, we make it negative. If it's negative, we make it positive. Very simple. Now reflections over the y-axis. Same thing, really. If we reflect a point over the y-axis, the original point and the reflected point have the same y-coordinate. They lie on the same horizontal line. So here are 2 points on the same horizontal line. The x-coordinates have equal absolute values and opposite positive or negative signs. So if we have a negative x value, it becomes positive. If we have a positive x value, it becomes negative. So in each case, the 2 points are reflections of each other. Negative 2, 5 is the reflection of 2, 5, and 2, 5 is the reflection of negative 2, 5. Now, a little harder, we'll think about the line y equals x. This line has a slope of 1 and a y-intercept of 0. It's a very special line. It makes an angle of 45 degrees with the x and y axes. As is obvious from the equation, this line is the set of all points in the xy plane for which the x and y coordinates are identical. There are no points for which the x and y coordinates are identical that are not on this line. And incidentally, a little piece of trivia, all the points above this line have a y-coordinate bigger than the x-coordinate. All the points below the line have an x-coordinate bigger than the y-coordinate. That's also something that can be helpful. Let's talk about reflections over this line. When we reflect a point in the xy plane over the line y equals x, the image has the x and y coordinates switched. So here, 2, 5 and 5, 2 are reflected images of each other over the line y equals x. In other words, we swap the place of the x-coordinate and the y-coordinate. That's the effect of reflecting over this particular line. Similarly, 2, negative 4 and negative 4, comma 2. Those would be reflections of each other over the line y equals x. Negative 1, comma 7, and 7, comma negative 1, also reflections over the line y equals x. And negative 3, negative 5, negative 5, negative 3, also reflections over the line y equals x. If we pick any pair of points like these, then pick any point on the line xy, then any point on the line y equals xy would be equidistant from those points because it's a point on the mirror line. And as we said above, any point on the mirror line is equidistant from the original point and its reflected point. Thus, for example, 1, 7, 7, 1, and k, k would form an isosceles triangle for any value of k, positive or negative. Because k, k It has to be a point on the line y equals x, a point on the mirror line. Any point on the mirror line is equidistant from a point and original point and its reflection. And obviously these 2 points, 1, 7 and 7, 1, are reflections of the line y equals x. So here we can get a visual of it, and we can actually see these various isosceles triangles. Here I picked just a few example points, but you get the idea. Any point on that line, the k, k could be anywhere on that line, and we'd get isosceles triangles. Although it's a rare topic on the test, we can also mention the line y equals negative x. This line has a slope of -1 and a y-intercept of 0. Like y equals x, it makes an angle of 45 degrees with the x and y axes. Also, like y equals x, this line has some special reflection properties. What happens when we reflect a point over the line y equals negative x? So here we have some examples. 2, 5 gets reflected to -5, -2, and 4, 2 gets reflected to 2, -4. So the reflection of 2, 5 is -5, 2. The reflection of 2, -4 is 4, -2. The x and y coordinates are switched, and each is given the opposite plus or minus sign. So any positive number becomes negative, any negative number becomes positive, and they are switched in their order. So that's exactly what happens. This can be a harder pattern to see, but if 2 points have been switched and opposite signed x and y and have switched and opposite signed x and y coordinates from each other, for example, -3, 5 and -5, 3, then any point on the line y equals negative x will be equidistant from both of them. Again, any point on the mirror line will be equidistant from both points. For example, -3, 5, -5, 3, and 12, -12 have to form an isosceles triangle. Again, the point on the mirror line, 12, -12, has to be equidistant from those 2 points. Here's a practice question. Pause the video and then we'll talk about this. Now this would be an example of a very, very hard question on the test. Ordinarily, this would be particularly hard, especially without a diagram. Now of course, you could probably sketch something and you get a ballpark idea, but it would be hard to verify it exactly. Well, we notice, though, that points J and K are reflections over the line y equals negative x, because we switched the x and y coordinates and we've made the 2 positives negative. 5, 2 and -2, -5. They have to be reflections over the line y equals x. So any point on the line y equals negative x would be equidistant from them. And so what's a point on the line y equals negative x with a y coordinate of 4? Well, it has to be x equals -4. We get the point -4, 4. So -4 is the x coordinate of L. In summary, we reflect over the x-axis, we keep the same x, we're on the same vertical line, we get opposite signed y coordinates. If we reflect over the y-axis, we have the same y coordinate, we stay on the same horizontal line, we get opposite signed x coordinates. Those are the really easy cases. If we reflect over the line y equals x, the 45-degree angle line, then we switch the x and the y coordinates. When we reflect over the line y equals negative x, we switch the x and y coordinates and we make each the opposite positive or negative sign. And in all these cases, the mirror line is always the perpendicular bisector of the segment between the original point and its reflected image. That's an important geometry fact. And most important, any point on the mirror line is equidistant from the original point and its reflected image. Finally, graphs of quadratics. This is another relatively uncommon topic on the test. Back in the algebra lesson videos, we discussed quadratics. As you may remember, a quadratic expression of x is any expression in which the highest power is x squared. If we set y equal to a quadratic expression of x, this would be a quadratic equation. So for example, this is a quadratic equation, this is a quadratic equation, this is a quadratic equation. All of these have a highest power of x squared. Now we can ask, what shape will we get if we graph one of these equations in the xy plane? Very interesting. Well, as you may remember from high school, the graph of a parabola, of a quadratic equation in the xy plane, is a shape called a parabola. A parabola is a very particular kind of U-shaped curve such as this. And I'll just point out, not everything U-shaped is a parabola. A parabola has a very specific curvature. Just as a circle is, not everything round is a circle. A circle is a very specific thing. A parabola is also a very specific thing. I'll also just mention, this is part of the magic of the xy plane, this connection that we establish between equations and shapes, that is, between algebra and geometry. Parabolas can open up or open down and can range from narrow to wide. So on the left we have a narrow parabola opening up. On the right we have a wide parabola opening down. Parabolas all have a vertical line of symmetry. What this means is if we start with any point on the parabola and reflect it over this line, the reflected image will be another point on the parabola. So the parabola, the purple parabola, is absolutely symmetrical. It is symmetrical over that green line, the line of symmetry. The line of symmetry always passes through the vertex. Now, on an upward-facing parabola, the vertex is the lowest point. On a downward-facing parabola, the vertex is the highest point. And so where the line of symmetry intersects the parabola is always the vertex. And if someone tells us the vertex, automatically they're telling us the line of symmetry as well. Here's a practice problem. Pause the video and then we'll talk about this. Okay. So we're told the vertex, so that automatically means that we know the line of symmetry. So the line of symmetry would be the line x equals 2. It would go right up the middle of this parabola. We have a y-intercept of 9. Well, let's think about this. That y-intercept is 2 units to the left of the line of symmetry. Well, where would the other point be? It would be 2 units to the right of the line of symmetry. So it would have a y-coordinate of 9 and an x-coordinate of 4. In other words, 4, 9. Sometimes the test will simply give you the graph of a parabola. Sometimes it will give you the quadratic equation and expect you to figure out something about the graph. As with lines, every point on the parabola must satisfy the equation of the parabola. That's actually a deep idea of the xy plane. Let's take a look at a particular equation. Suppose we have this equation and we want to find points on this equation. Well, a very easy way to do this would just be to plug in some values. So for example, we plug in x equals 0, we get y equals 4. We plug in x equals 1, we get y equals 3. Plug in 2, we get 0. Plug in 3, we get negative 5. We should also go in the other direction. If we plug in negative 1, we get 3. We plug in negative 2, we get 0. If we plug in negative 3, we get negative 5. So we certainly see some symmetry emerging here. And in fact, if we plot these points, then what we'll get is a graph, and it will be very clear that 0, 4 is the vertex, and the line of symmetry is the y-axis. Standard form for a quadratic equation is y equals ax squared plus bx plus c. When a is greater than 0, the parabola opens upward. And when a is less than 0, the parabola opens downward. So we can tell whether it's an upward or downward opening parabola purely by the sign of the quadratic coefficient, the coefficient of x squared. When the absolute value of a is greater than 1, the parabola is skinny. And when the absolute value of a is less than 1, the parabola is wide. So this gives us a way to look at a and tell relatively how skinny or wide the parabola is. When y equals 0, of course, those are the intercepts. These are the solutions of the quadratic equation 0 equals ax squared plus bx plus c. Recall that a quadratic equation can have 2 or 1 or no solutions. And graphically this makes sense. We could have a parabola that intersects the x-axis twice, or once, or not at all. Here's a practice problem. Pause the video and then we'll talk about this. A parabola has an x-intercept at -4, 0. If the vertex is at 2, 5, find the other x-intercept. Well, this is interesting. Because we know the vertex, we know the line of symmetry. The line of symmetry has to be x equals -2. Well, let's think about this. The point -4, 0 is 6 units to the left of the line of symmetry. So its reflection would have to be 6 units to the right of the line of symmetry, and so that would be the point 8, 0. And that's the other x-intercept. So notice that all we had to do was think about symmetry. We didn't have to do any elaborate calculations. Here's the picture just to verify what's going on. The graph of a quadratic is a parabola. If a is the quadratic coefficient, the multiplier of x squared, then if a is positive, that means that the parabola opens upward. When a is negative, it means it opens downward. If it has an absolute value greater than 1, then the parabola is skinny. If the absolute value of a is less than 1, then the parabola is wide. The x-intercepts of the graph are the solutions of the quadratic set equal to 0. And those are the big ideas of quadratics.